Hi there, I'm Patrick Stewart, and I am solving a statically indeterminate problem. I've already started it a little bit because I screwed my video up the first time, but this is our problem. We have a bar in between two walls with a ring around it providing a force to the right. We're looking for our reaction forces, and I've drawn those in. We've got RA going to the left and RC going to the right. The force is 500 pounds, the length of the first section is 8 inches, the second section is 2 inches. So the first thing we want to do is our force balance equation, and since there are no y forces, we're just going to sum the x forces. So 0 equals negative RA plus F plus RC. And if you want to real quick solve for RA, you can find that it equals F plus RC. And similarly, if you want to solve for RC, you can find that it equals RA minus F. So now our second step is to do the force displacement equations. And I got those straight out of the book. Delta equals PL over AE. And we'll call this delta 1, will correspond to that section, and we'll call this delta 2. So delta 1 equals P1 times L1 over AE, and delta 2 is the same thing, P2 L2 over AE. And third step is to do these compatibility equations. And since this thing is fixed between the two walls, we know that its final length is going to equal its beginning length. So the displacements, delta 1 plus delta 2, must add up to 0, since the final length is going to be the same as the original. Taking a look at that, we can see when we plug these two equations into equation 3, we're going to be able to cancel out AE. AE is the same for the whole bar up here because they have the same diameters, so they have the same cross-sectional area, and the material is constant throughout, so they have the same modulus of elasticity. So we'll do 2 plus 3. We'll cross these guys out real quick, and we get P1 times L1 plus P2 times L2 equals 0. So now the only thing we don't know is P1 and P2, which are the axial forces within this thing, and we've got to do these little cut pictures, kind of like Heinrich does in class. So the first section is right here. Draw that in. And I've already drawn that down here. So we sum our forces, and we get 0 equals negative RA plus P1, or RA equals P1. Alright, now we got to do this next section. So we'll draw this up there. And I have already drawn it down here, although we need to put in our F and our P2. And then we're going to sum the x forces again. So 0 equals minus RA plus F plus P2. Sorry about the shaky camera. I had a little too much coffee today. So we can see that P2 equals RA minus F. Gosh, this thing is really shaking on me. Okay, so now we can plug those into the things we already had before, the P1 L1 plus P2 L2 equation. So we get RA times L1 plus parenthesis Ra minus F times L2 equals 0. Then we distribute the L2, so we get L2 times Ra minus L2 times F plus Ra times L1 equals 0. And then we're going to move this thing over to the right side and factor out the RAs. So we've got RA parenthesis L1 plus L2 equals L2 times F. Then we can see that RA simply equals L2F over L1 plus L2. And we know all those numbers, so let's plug them in real quick. We've got 500 pounds times 2 inches divided by 8 inches plus 2 inches, and that equals 100 pounds. Now, if we go back to the beginning where we said that RC equals RA minus F, we can do RA minus F because we know those. That equals, we just found RA is 100 pounds, so 100 pounds minus F, which we know is 500 pounds. That equals minus 400 pounds, which means that our RC was written in the wrong direction. Oh, we should say this is RC. So, we found our two reaction forces, and we can kind of see that this one was in tension and this one was in compression.